Hi, as part of this week's review video, today I'm going to be going over how to use BFS, or breadth first search, to find a shortest path tree within your graph. Um, we kind of went over a problem similar to this in this past week's section, but if you were unable to attend or if you wanted more practice on how to do that, then this is the right video for you. So what is breadth first search? Well, it's a way of searching a tree or graph where you start at a source um, marked by this S, it's node 0, and then you go level by level, methodically searching the whole level before you proceed to the next level and then the next level. Um, it's as opposed to DFS, depth first search, where you would just go all the way to the end and then backtrack and then try another path all the way to the end. For instance, depth first search would look like, I don't know, you go here and then here and then here, we've reached an end, and then you backtrack to this 4, you go now here, 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 and you got a couple choices, you could do like that. That's kind of what that looks like. Whereas a breadth first search would be like, you go to this one, and then you look at both of one's children, and then you try this child, and then you try this child, or sorry, you would try this and then you go here. Um, so it's like you literally process each level at a time rather than each whole path to the end as a time at a time. The important part to note is that the fringe or perimeter data structure that you use to determine what you pull as your next node to search. In a breadth first search, that is a queue. And in depth first search, that is a stack. That's an important distinction there between those two. Otherwise, the rest of this code, especially this part, is pretty similar. Um, that's just the key distinction on how to do breadth first search. I mean, there's many ways to do breadth first search, but the way we're doing it, that is the distinction between depth and breadth first search. And in order to find a shortest path tree, you need to keep track of each node's previous item. And there's many ways you can do this. This pseudocode doesn't tell you exactly how, um, but basically you'll need a way to map the current node that you're processing to the node it just came from and be able to access that multiple times. And you also want to keep track of your distance along the way. In these graphs that are, in this graph that I'll be showing you for this problem, it's an unweighted directed graph. And since it's unweighted, we're not assigning any sort of distance to it. It's just that each link has a distance of 1. So it's like how many links it took you, or how many edges it took you from going from the start to this current node. But essentially, it's pretty much the same code, except you have to keep track of distance along the way, like here and here, and map backwards your current node to your previous node. That's a bad underline. There you go, like that. And the pseudocode doesn't tell you exactly everything. Like there's some things that would not work, I think. But it should give you a pretty good idea on how to implement this yourself. Maybe it does run, actually. It looks pretty good for pseudocode. So let's look at an example, kind of similar, again, to what we did in section. So A is going to be our source node that we're going to start at. That's why it has a star next to it. And that's also why we have it in our queue to start with. Our queue needs to start with something, so it's going to start with that source. So our first step, we're going to pull the A and then look at its children. We pop the A from the queue, and we see its children are B, C, and D. In no particular order. I'm just going to do it in alphabetical order. I don't know how your algorithm would look at it. B, C, and D are now in our queue. We can say A does not have a predecessor because it's the source, and now A has been processed. So we move on to B. We pop B from the queue. We see that B just came from A. You would need a way to keep track of that. B just came from A. B's child is D, but D is already in our queue that we still need to explore. So really nothing else happens there. So we're good. Next, we pop C. C doesn't even have any children, so there's nothing to add to the queue. We know it came from A, so we've got that. now is the predecessor there, and C is now done. And now we move on to D. So D, it just came from A as well. So we have A as the predecessor, and its children are E and F. So we pop the D, so that should be out. So it has E and F as its children. We mark that as processed. The order in which I'm doing things may not exactly reflect what you should do in your code. This is just kind of like the general algorithm. For instance, when we're popping the E, you might want to mark it as processed as soon as you pop it. So that way this link doesn't actually trigger and put E back in the queue, for instance. So we mark E as processed. That way we don't put it back in the queue like that, because we don't want to do that. That create an infinite loop. So mark E is processed. We see its children are E, which has already been processed, so we don't count that, and F. F is already in the queue, so that's fine. And it just came from D. And F, remember we took this link from D. We didn't actually take this link from E. So that's why we're going to say F has been processed, and it came from D. So that makes sense. You just go level by level, and you compare, or you see what node it just came from, and you write that down. You mark it as processed, and then you repeat that. It's a pretty short, simple algorithm, and it gives us this table. And then from this table, we can create our shortest path tree. So what is a shortest path tree exactly? Well, basically, it's kind of going to be a sub-tree of your tree or graph. So it's going to be like a subset. It's not going to contain every single edge necessarily, but it's just going to say from your source node, which is our A, to each other node, what is the shortest path. So for instance, we're going to get rid of, in our shortest path tree, we're going to get rid of edges like that, because that's not going to be the fastest way to get anywhere. You're not going to even use that edge. So we're going to use this path to get or use this table to get our shortest path tree. So we see A didn't come from anywhere because it's a source. B came from A. B came from A, so that's a significant edge. C came from A. That's also a significant edge. And D came from A. That makes sense. Those edges are all necessary in order to get to those three nodes. There is a way to get B to D, but C and B you can only get from A, and A to D is the fastest way to get to D. So you can check that makes sense. To each of these nodes, that is the fastest path to get there. And then E comes from D, so that's this edge. And F comes from D as well, so that's this edge. Oops, let me draw that better. F comes from D. I did not draw that any better. There we go. So that's that edge. And that is our shortest path tree. As you can see, we eliminated edges that do not speed anything up, such as this one, and this one. They don't get used at all in our shortest path tree. So that's how that works. You can just use BFS with a slight modification as shown here. I'm not going to give you exactly the code because it may be important for you to code up. Hint, hint. But basically, you can just use BFS to search through each level, find each node's previous node that it came from, make sure you do things in the right order, put them in the queue, pop it out, mark it as processed, all that stuff. And then from that table of each node to its previous item, you use the links that mark those, or the edges that mark that relationship. So B's previous is A, so that's this edge. You use that notion to get each of those edges that are significant in your shortest path tree. And then that's it. You've got your shortest path tree. What you do with that is up to you, but that's how you make it.